Hello and welcome to Honors Function. After exploring where the logarithmic functions are from, let's now turn our attention to their graph. So recall that the exponential base a has r for domain and 0 infinity for range. Therefore, the logarithm base a will have 0 infinity for domain and r for range. You take an x and you associate log base a of x. So that means that any real number, so if you take a real number k, okay, if k is a real number, you can find an x so that k is equal to the log base a of x, because the range of log is all real number. Any real number can be written as a log. That's a very important property, okay? Let's look at the graph of logs now. And let's first recall how to construct the graph of an inverse function. So you probably remember that to draw the graph of an inverse function, you need to draw the symmetrical with respect to the line of y equals x of the graph of the function, okay? So let me quickly remind you how to draw a symmetrical graph. Let's take a point uv on the graph of the function. Now this is a point uv, so what I want to find is the point vu. How do I find vu on this plane right here? Why do I use the line y equals x? So check it out. This is the point uv, therefore this is u and this is v. Now if you use the line y equals x, you can report that u right here on the y-axis, and you can report the v right here on the x. This is v. Therefore, vu is right here. That's the point vu right here. And the 2 points are symmetrical with respect to the line y equals x, so it should be a right angle here, and the distances are the same. Okay? So the graph will have, so let's see, if the x-axis is the horizontal asymptote of y equals a of x, then the y-axis will be the vertical asymptotes of the log base a of x, right? And here's the log base a. Now, you remember that the exponential graph is one of the fastest increasing function. Well, therefore, the log graph is going to be one of the slowest increasing function, okay? But it always increases. You do not have a horizontal asymptote here. It always increases, okay? Very, very slowly. Now, what's the point right here? This is 0, 1. Therefore, what's the point right here? This is 1, 0. Also, the other characteristic point on the graph of the exponential is 1, a. So actually, let me erase all of that here. Let me erase this one too. Let's call this point, let's not say u and v, but let's assume this is 1a, okay? Then if this is 1a, on the graph of the log, we should find a1. Here we go. So these 2 points are standards on the graph of any log. All right? So quickly, right here, let's look at the graph of ln of x. So ln of x is going to go like this right here. And of course, you have the point 1, 0. And you will have the point. So here you need 2.71, right? So if this is 3, this is e right here. And then that's going to be 1 right here. Okay? So you have e1 right here. And the other log, the decimal log. So this one will still go through 1, 0 right here. But now, the other point is much further down. 2, 3, 4, 5. Oops, I need more. 6, 7, 8, 9, and 10 right here. And you move by 1. So you start seeing how, as the base increase, these graphs are really, really moving up very, very slowly. Okay? Very slowly. All right, let's quickly check out the property of these logs. I wrote them all in my notes. Here we go. These property of logs are pretty standard. Of course, the one-to-one property is the one we use to solve equations in log, okay? Equality of output imply equality of input. Let me show you right now all the various logs I've graphed. It is not going to be common at all, actually. I can tell you right now, I am not going to look at the base smaller than 1. And actually, the main base for log is ln, okay? So the graph for logs will all be increasing. What do you do if you have a base smaller than 1? It's always possible to change it to get an increasing base, okay? An increasing graph. I'll show you how. Okay, let's look at some examples now. All right, I'm going to let you do the first and the second example, and we're going to start with the third example. You want the domain of this function. So the domain of g is made of all the x's, so that x squared minus 5x plus 4 over x plus 2 is strictly above 0. Now, the sign of a ratio is the same as the sign of a product. So instead of looking at this ratio right here, I'm going to be looking at the product. X squared minus 5x plus 4 times x plus 2, right? The property of signs for a ratio are the same as the property of signs for a product. Therefore, solving this inequality will be the same as solving this inequality. X squared minus 5x plus 4 times x plus 2 strictly above 0. And solving this inequality is not difficult after covering polynomial functions. Check it out. Let's factor the first. So it's x minus 1, x minus 4 times x plus 2. So what is this? This is a polynomial, right? Polynomial. The degree is 3, and it's a positive leading coefficient. Therefore, the graph is going to go like a line going up. Where are your x-intercept? Well, 1 is at here. Let me get my negative 1, negative 2, 1, 2, 3, 4, 5. Okay, x-intercept. You got one at 1, another one at 4, 3, 4, and then the last one at negative 2. And the graph goes like a line going up. So it's like this, and like this. All right, I got it. Positive between negative 2 and 1 and above 4. So the domain of G is everything between negative 2 and 1, or everything above 4. Here we go. Not too painful, is it? Let's go over another example now. All right, example number 5. Same question about the domain. So here you're going to have to be careful. You first must guarantee that negative 2x squared plus 3x plus 2 is positive, but at the same time, you have to guarantee that 2x minus 3 is not 0, okay? All right, let's take care of this inequality. It should be a piece of cake. 2x squared minus 3x minus 2 has to be negative, right? And multiplied by negative 1. Let's see if we can factor that. 2x, x, 2, minus, plus. Okay, so what do we have here? We have a parabola, and it's concave up, and we want it to be negative, right? Okay, quickly, let's check it out. So negative 2, negative 1, 1, 2, 3. All right, the intercepts are negative 1/2 right here and 2 right here. And we want it to be negative, therefore it's everything between negative 1/2 and 2. So the domain is everything between negative 1/2 and 2. Do we have anything to remove from there? Well, let's see. X cannot be 3/2, and that is actually in there, right? So we need to subtract 3/2 from there. Of course, we wouldn't really leave it like that. We would write it as negative 1/2, 3/2, union 3/2, 2. Okay? All right. Let's go over another type of examples now. So here we have to solve an equation. We're going to have to be very careful here. Be careful of the domain. Okay? So be careful of domain, because these are logs and they're not defined just anywhere, right? But before I wonder about that, let me fetch my solution. Equality of output implies an equality of input. So x squared minus 2x minus 3 has to be the same as 1 minus x. Okay, the log is a one-to-one function. So this is the same now as what? X squared minus, so actually that's minus x, right? Plus x, and then minus 4. And that is equal to 0. So you cannot factor that, so we're gonna need to, I'll complete my square. X minus 1/2 squared minus 1/4 minus, so 4, that's 16 over 4 equals 0. Therefore, we have x equals, so 1 and 16, 17. So root of 17 over 2, right here. And then here we have 1/2. All right, root of 17 over 2. Now, we need to be careful. We need to make sure we are in the domain. Root of 17 is about 4, right? Is about 4. So root of 17 over 2, root of 17 over 2 is about 2. So these two values are 1/2 plus 2. So it's about 2.5, about, okay? So this is about 2.5. And the other one is negative 2 plus 1/2, so it's about negative 1.5. So let's look to see if we have some extraneous solution there. All right, let's look at this one right here. So 2.5 is not going to work, right? 1 minus 2.5 is going to be negative. So already this I have to eliminate, okay? Again, why? Because if you do 1 minus 2.5, that's going to be negative. And you can't have something negative inside of a log. That's because of the domain. So this is gone. What about the other one? What about negative 1.5? Well, negative 1.5 works for this, right? 1 minus negative 1.5 is positive. Now, what about for this? Does it work or not? Well, how about we check out the domain of this right here. So this is x minus 3 x plus 1, right? That's you know, the inside. X minus 3x plus 1. And if you look at the parabola, it's a parabola that is concave up, so negative 2, negative 1, 1, 2, 3. It's a parabola that is concave up. The x-intercepts are negative 1 and 3, and it's concave up. So it's defined below negative 1 and above 3. So negative 1.5 should work. Therefore, the only answer is x equals 1/2 minus root 17 over 2. Okay, that's the only solution. All right, let's do two other problems about graphs and we're done with this video. All right, here's another typical question that we have encountered with exponential. Determine the domain, range, equation of the asymptote, increasing and decreasing interval, and the limits. Now we're gonna have to be careful of the limits right here. The domain is not all real numbers, so we'll have to pay attention how we write the limit, okay? What do you start with? I'm gonna quickly do some graph shifting here. I'm gonna be very quick about it, okay? So here's what I start with. I start with ln, and it goes like this, all right? I don't need to be more careful than that. That's fine. That's y equals ln x. Okay, next, what do? You go 3 to the left. Now, 3 to the left, so let's do 1, 2, 3. And this is where you will have the vertical asymptotes, right? There would be a vertical asymptotes right here. 3 to the left, here we go. 3 to the left, ln, right there. Okay, so this is y equals ln of x plus 3. Now what do? Here, you reflect across the x-axis. Okay, so now that's going to reflect this vertical asymptote. So 1, 2, 3. Here's going to be now my vertical asymptotes. So my graph is going to be at, so where I am. So this goes like, it's really not very good what I've done, okay? Something like this, right? Okay, here we go. So this is y equals ln of negative x plus 3. Here we go. Now, the multiplication by 2, that's not going to change very much. It's just going to go higher this way, and it's going to drop quicker here. But the asymptote is the same, right? The asymptote will be the same right there. That's going to reflect it. Now, that's going to change a little bit. So now my graph is going to go the other direction, okay? So it's going to go like this, right there. Sorry, it's getting a bit messy here. And then I move up 1. I really don't care about moving up 1. I'm not going to change anything. So let's answer this question. So domain, all right. Well, we see the domain. The domain is negative infinity 3. Okay, negative infinity 3. That's your domain right here. We could have looked at that and say negative x plus 3 has to be positive. It would have given us a domain too. Okay. The range, it's always the same. For log, it's all real number. Asymptotes, we have a vertical asymptotes. It's x equals 3. The function, that's my last one right here, plus 1, of course. The function is increasing on its domain. Increasing on its domain. I guess we need a shortcut for that. We should say monotonously increasing. Okay, whatever. And finally, let's describe the limits. So the limit of, what's the name of the function? The limit of f of x as x approaches negative infinity, well, it is, okay, it's going really super slowly, but it's going to go to negative infinity, okay? It's going to take billions of light years, but it's going to get there. And it's going to go further down. The limit as x approaches, now be careful right here, it is 3 from the left, right, of f of x is positive infinity, okay? There's a vertical asymptotes. Okay, one more problems and we're done. Follow me. Here we go. I want to precisely graph this function. I'm telling you to apply the graph shifting result, but actually I am not going to, okay? So first, I'm going to grab my vertical asymptotes. It's always at the edge of the domain, okay? So if you make this equal to 0, you're going to get your vertical asymptote. So x equals 2 is the vertical asymptote. So let's go. X equals 2, vertical asymptote right here. And then I'm going to grab 2 points, okay? The first point is for 2 minus x equal to 1, right? You remember on the graph of a log, you want 2 points. The first one is when the input is 1, because the output is always 0. And the second one is when the input is the base, okay? Because the output is always 1, right? The A1 right here. So this is the first one, okay? If the input is 1, the output is 0. So this happens where? It happens at x equal to 1. If x is 1, the output of the log is 0. So that would be going towards 0. And therefore 2 times 0, 0. So y is 2. If x is 1, y is 2. Here we go, right here. And the next point is for the whole input to be equal to the base. So I want that to be equal to the base. So 2 minus x equals 5. And that is telling you that x is negative 3. And if x is negative 3, what's the output? So if this is 5, the output is 1 right here. 2 times 1 is 1. 2 times 1 is actually 2. 2 plus 2 is 4. So at negative 3, you are up 4 right here. And this is fine enough to draw a pretty graph of this function right here, right there. Something like that, okay? That's it. Thank you for watching.